Okay, so number 10. Okay, so put your heading on, fold it up, get the fringe off. So no fringe, please. So this is the key. So if a full circle is, it tells us that a full circle is 240 barks. That's all you need to know if you understand percent of the circle. We can do any conversion that we want using percent of the circle. So it says, okay, so creating a protractor. So creating a protractor just means then how do we decide how these go? Where do these go to design a protractor to do that? Okay, so what we need to know is we need to know this distance right here. So if we had this distance, then how would we know how far apart to space these? So how many barks? So a protractor then shows half of a circle, right? So how many barks would we have around half of the circle? 120 barks. So if you knew the half of the circumference, which would be that length right there, how would you decide how far apart to put the little marks for each bark? Yeah, so you would just take whatever this half circumference is, 1/2 of the circumference of your protractor, which would be this distance right here, and you do what? Divide by 120. And that would be the distance that you'd have to go along the edge of the protractor. That'd be the distance you go along the protractor from one bark to the next, would be half the circumference divided by 120. Does it make sense? Okay, so then it says, how many radians are equivalent to 200 barks? How many radians are equivalent to 200 barks? What do? We've got 200 barks. What do we find first? What did I say? Angle measure is all about percent of the circle. So all we got to know is what percent of the circle is 200, and then we'll have that same percent of 2 pi. So what percent of the circle is 200? 200 over 240. Find that value, which is 10 over 12, right? Divided by 20. 0.833. Okay, so 200 barks is 83.3% of the circle. So how do we find how many radians it is? We're going to take that number of barks, or that percent of the circle, times, we want the same percent of 2 pi. What is that? 5.24. About 5.24 radians. So percent of the circle, then times a full circle in radians gives that angle in radians, which corresponds to that same percent of the circle. So really, we could have just taken that 200 over 240, which is the percent of the circle, multiplied by 2 pi. We never have to know that percent. We just have to know that that ratio represents that percent. Multiplied by 2 pi, we get 5.24. Okay? A function that converts the number of degrees to the number of barks. So if we had the number of degrees, what would we do first? So let x be the number of degrees. And what's the process? To get to barks, we'd start by doing what? divide by, this is the number of degrees. We want to get percent of the circle. So we'd start by dividing by 360. Okay? And so that would be the fraction of the circle right there, or the percent of the circle. And we want that same percent of what value to get Barks? 240. So this would be our rule. So if the f function converts, what does it do? It converts degrees to Barks, because you take the degrees, you find the percent of the circle, and then you're going to take that same percent of a full circle in Barks. And that will give you the corresponding angle measure in Barks for x degrees. So input degrees, output Barks. This gets you percent of the circle. Multiply it by a full circle of Barks, and you get the corresponding number of Barks.
So then for Barks to radians?
Piece of cake. You start with Barks, so we'll call B Barks. How do you get percent of the circle?
40 times 2 pi.
Yeah. So this would convert. So G of B would take Barks. It would make the percent, and then times 2 pi would give you the number of radians. So then if we had, this is Barks, right? So we could put, they're saying we could put the output of this function into the input of this, right? Because the output of this is Barks. It's also the input of this. So G of f of x would do what? Would take degrees and output radians. It would, so with Barks in the middle, it would be degrees to Barks, Barks to radians. Right? Make sense?
Yeah. So that's E then.
That'd be part E. Yep.
E.
Okay, 21. So in 21, I just happen to have a picture of that. Okay? There's the fan, there's the bug. What's the radius of the fan? In this is number 21. Is the radius 2.6? 2.9? 2.9. So it says, if the bug swept out 1.23 radians, how many feet did the bug travel along the arc? So radians, so we can deal with any angle measure, but we like radians for, there's a very special thing that radians can help us with. What is a radian?
Radian is one measure.
What's that? The rays of the angle. That's right. So if it's 1 radian, if I have an angle of 1 radian here, that means that the rays cut off an arc length of 1 radius length. So the convenient thing about radians is we have this direct relationship to arc length. That's why radians are very advantageous, because you have this direct relationship to radius length measured in terms of the radius. Okay, so arc length measured in terms of the radius. Okay, so if it says 1.23 radians, so if you have an angle of, so say we go, I'll take it back here. We'll get 1.23. That's the closest I can get. Okay, so here's our starting, the positive x-axis. So the bug has gone an arc length, or has gone 1.23 radians, right? And it's asking how far did the bug travel in feet? So if you understand radians, this is a piece of cake. What does the 1.2 radians mean? What does the 1.23 radians mean? Tell the person next to you. Tell the person next to you, what does the 1.23 radians mean in terms of the distance the bug traveled? Go. Tell me, what does 1.23 radians mean?
The times that radius has been.
What's that?
It's like the amount of times that the radius has been traced upon the outside of the circle.
Right, exactly. Okay, so what it means is, it means that this arc length right here is how many radius lengths? 1.2 radius lengths. So if you measured that arc that the bug traveled, in terms of the radius, it would have gone 1.23 radius lengths. Okay, that's what 1.23 radians means. So therefore, how many feet is that? If each radius is 2.9 feet, so one radius equals 2.9 feet, then how would you find how many feet it went? It went 1.23 of these, right? It went 1.23 of those. So the number of feet would be 2.9 feet, or sorry, 2.9, which is one radius length times the number of radius lengths. And tell me it again. 3.57 feet. And this goes back to the general formula that the radius times the number of radius lengths, which is the same as the angle and the value is the same as the angle in radians, equals the total arc length. So when you work with this equation, don't just plug and chug. The whole point is that this represents two different things. It's the same value representing two different things. What two different things does that theta represent? The angle measure in radians. You can also think of it as then, if it's radians. What else?
Percent.
No?
It's degrees.
What else does it represent? How many radius lengths of arc length you went? It's the same number. The number of radius length and arc length. The number of radius length and arc length is the same as number of radians that the angle would cut off. So that theta, you can think of it interchangeably as number of radius lengths of arc length or the angle in radians, because they're the same value. Okay, so if the bug travels 2r feet, how many radians did it go? Is that what it's asking? So it's saying it went 2r feet, or what is that? 2 radius lengths.
2 radians.
So how many radians did it travel? 2 radians, right? Because it's 2r would be 2 times the number of radius lengths. And that's exactly what radians is. Okay? It's the openness for an angle measure of 2. Okay? It's really easy when I say it, but you have to practice it in different scenarios. Okay? So make sure you really practice it in different problems. You know, given the number of radians, what's the length in feet? Given the number of feet, what's the radians? Keep practicing and have someone to talk to when you do it. Okay. So we're going to keep talking about the bug on the fan here. So here's the bug on the fan, and our goal here is to have a way to pinpoint its location at any point in time. Okay, so what quantities, this was your number 19, what different quantities, changing quantities, might we keep track of that would help us say the bug is at a certain location? So what's an idea of a quantity we might track here, a changing quantity we might track to keep track of the bug's location? Number of radians, the angle that the bug's gone through. Would that be a good one to track? Definitely, okay? So we can think of that this way. Okay, so this is representing keeping at any given point in time, keeping track of how many radians the bug has rotated through. Okay, so right now the bug's rotated through 3.4 radians. How many feet has it traveled? If it's rotated 3.4 radians, how many feet of arc length has it traveled? Everyone do it. So each radian is 1 radius length. So 3.4 radians would be how many feet? Is that times 2.9? 9.86. Okay, that was just kind of a side note. But really what we're talking about here is monitoring the position of the bug. And so certainly the angle is going to be important so given a certain current value of the angle, that can help us nail down where the bug is for that angle. Okay, what other quantities might we think about in terms of where the bug is at this is a variable speed fan. Variable speed fan. Okay? So sometimes the speed slows down, speeds up. So what else would we monitor to say, at this point in time, this is where the bug is? Okay, how fast it's going? We could look at that. What else? We want to pinpoint its location. How do we do that? How do we use values to say this is the location of the bug? The location relative to what? Okay, the start of the circle. So what, like distance from the start of the circle? Okay, so what if we thought about the horizontal diameter of, what is the rotation of the bug? What's the path of its rotation? Circle, right? So what if we thought about the horizontal diameter? So what would we be tracking relative to the horizontal diameter? In order if we want to pinpoint the location, so what could we do relative to the horizontal diameter? Arc length, okay. Let's say like if I stopped it right here and I said, what's its position relative to the horizontal diameter? What would you imagine? What's that? Yeah, so like, you said the y coordinates, so like, it's vertical distance, okay? So we're talking about angle. So angle in radians. Okay, and then we can talk about the vertical distance above the horizontal diameter. Because that's a lot, I abbreviate all those words. Vertical distance above horizontal diameter. So if I'm saying above, then what would this be? So if we were measuring horizontal distance, vertical distance above the horizontal diameter, what could you say about the value of that quantity right now? It would be negative, right? So if we're defining it as above, then we're just saying that above is positive, and whatever it's below, we'll just put a negative sign, and that will tell us it's below, right? Okay, so then what else could we track? Yeah. Horizontal distance from what? So we could have a vertical diameter, right? And we could track the horizontal distance from the vertical diameter. So we would have to specify then to the right. Horizontal distance right of the vertical diameter. So we can do, and then if we look at all those things together, we can get the exact location of the bug for any angle. So the angle is going to be what? Input or output? Input. It's like we're going to say, okay, we know that the bug has gone through this much angle. That's our input. Okay? And then our output for an angle could either be this vertical distance above the horizontal diameter or a horizontal distance to the right of the vertical diameter. So with those two relationships, with those two functions, we can just, here's the angle of 2.89. If we knew the vertical distance at 2.89 above the horizontal diameter, and the horizontal distance to the right of the vertical diameter at 2.9, we'd have the exact location of the bug, right? We'd have it. You look so sleepy, so bored. This is so good. I worked hard on this. Okay. So what about the horizontal distance to the right of the vertical diameter for this angle, 2.89? What about the horizontal distance to the right of the vertical diameter for this? It's not to the right, it's to the left. So how can we measure its distance to the right? Negative, right? So here, that horizontal distance would be negative. What about the vertical distance? Positive, right? Okay. So this is what we want to do. So we're in worksheet 3. Go ahead and open up to worksheet 3. Page 273. So I want you to note that now the fan is 2.6. The radius is 2.6. So it was 2.9 in the homework, but now the radius, let's just note it so we don't forget. The radius is 2.6 feet. Okay? Okay, so I'm going to, in terms of numbers 2 and 3, that's going to be more review homework for a week from today, okay? Because that stuff's really important. But we've already covered it. We want to move on. So now we want to really break this down. So how do we see that relationship, say, between angle, and let's start with vertical distance above the horizontal diameter. So what was our strategy for really understanding the covariation of two quantities? We had a very specific strategy that we took. Do you remember what that was? What's that? No, so given any two quantities, we want to break down and really analyze and see how those are varying together. We had a very specific strategy to do that. It was a procedure that we had to help us do that. Remember what it was?
That's like the radians to degrees and degrees.
No, that's converting angles. So any two quantities, and we want to find out how the one quantity is varying relative to the first. Remember what we did? What we did was we said, let's take small equal increments of the first quantity. And so what's our first quantity here? That we're going to take small equal increments. What am I showing there? Equal increments of what? Okay, so what is this, the quantity I'm showing equal increments of here? Not degrees. We're going to measure the angle in radians, okay? So this is showing that the angle measure, I'm going to break up the angle measure into equal amounts of angle. okay? And we're going to use radians. But in fact, what we're going to use is, to make it even easier, is each one of these angles is 1/16 of the circle, because I've got each quadrant broken up into 4. So each angle is 1/16 of the circle. Okay? And then from there, what did we do? We looked at the other quantity, and what questions did we ask about the other quantity as we increased the first quantity by small equal amounts? What questions did we ask? Remember?
Increase y equals 3. Increase.
Okay, so what is our output quantity? We want to look at vertical distance first. So our input is the angle swept counterclockwise from the positive x-axis, and we're going to use 1/16 of a full rotation. So this is what angle? If we're using 1/16 of a full rotation. That's 1. That's the angle 1. What's this? 2, 3, etc. 4. And 4/16 is 1/4. 1/4 of the full rotation. Okay? This would be how many 16ths? 8, which would be half of the circle. Okay? The output quantity is going to be, we're going to look at first, we're going to look at vertical distance above horizontal diameter in feet. So what would this measure of it up here be? How many feet would this be? Vertical distance above horizontal diameter. Right, 2.6 feet. That would be an output of 2.6 feet. What would it be here? What would be the vertical distance above the horizontal diameter right there? 0, right? It's on the diameter. Okay, what about down here? Negative 2.6. And what about the starting point? 0, okay? So that's going to be our output quantity. And these are the questions we asked. So for equal increases in input, we asked, does the output, first of all, does it increase or decrease? So does the output go up or does it go down? But then the harder question, and the one that caused us to think a little bit more, do changes in the output increase or decrease? Remember doing this? Remember this with the bottle problems and the polynomials? So this is how we're going to analyze, and we're going to figure out what the covariation of vertical distance above the horizontal diameter is relative to angle. Okay, by increasing this one thing at a time. Okay, and then we said to help us answer that second question, do the changes increase or decrease? We asked about the changes. Are the changes becoming more positive? Are they becoming less positive? More negative? Less negative? Okay? So by asking, if we're stuck on this, are the changes increasing or decreasing? Remember there was this kind of counterintuitive thing that happened, right? So that we can ask the sub-question, are the changes becoming more or less positive or negative? Okay, so let's give it a go here. We're going to track. We're going to go one angle measure at a time, and we're going to track the vertical distance. And we're going to ask these questions each time. So here's the first 16th angle. Okay, and so did the vertical distance, first question, did the vertical distance, did it increase or decrease? Increased. Okay? And we're going to do it again. Next angle, 2/16. Did the vertical distance increase or decrease? Did the change in vertical distance increase or decrease? What do you think? What? So let's do the next one and it'll tell us for sure. So I'm going to do the next angle. Does the vertical distance still increase? What about the change in the vertical distance? Decrease. And so one more time to the top. So in the first, so this is on page 274. We're going to skip A. A should be at the end, right? We got to do B first. We do B first, and then we're going to go back and make the sketch. Okay? So as the bug goes from the 3 o'clock to the 12 o'clock position, what happens to the vertical distance? It increases from what to what? From 0 to? No, that's the angle, but what does the vertical distance go? From 0 to what? 2.6. 2.6. It goes from 0 to 2.6. As it does that, what about the changes in height? The changes in height do what as the height increases from 0 to 2.6? They decrease. Do you see that? And I'm showing that there on the right. Each time we advance the angle, we get a change, but each change is how compared to the last one? Less positive, right. Each change is less of a positive change than the one before. So now, how, if we were to graph that, just from the angles from 0 to 4/16, what would that graph look like? So now, here on the x-axis, I'm going to put angle. So now we think of the angle increasing this way across the axis, and then the corresponding change in height on the y-axis. So what will happen, we'll start at this point, 0, 0, right? Because when the angle is 0, the height is 0. So I'm guessing, I'm not sure, but I'm guessing it's about here where we're at 1/4/16 angle. So at 4/16, what is the height above the vertical diameter, or the vertical distance above the horizontal diameter? 2.6, right? So we know it's going to increase from 0 to 2.6 as the angle changes from 0 to 4/16 of a rotation. How will it do that? That's the question. So that has to do with the changes. He wants concave down. Yep. Because if the changes are decreasing, then the first change is going to be the most. And then each subsequent change, we're going to see less of an increase in that vertical distance. Oh, I got it pretty good. Okay, so now I want you to do on part B, I want you to write about going from 12 to 9, 9 to 6, and 6 to 3 o'clock position before you're doing the graph. And you can watch. I'll spend like a minute on 12 to 9, and then a minute on 9 to 6, and then a minute on 6 to 3. You can watch what I'm doing, and you're writing in, answering these questions. Does the output, or the vertical height above the horizontal diameter, does it increase or decrease? What do the changes do? Do they increase or decrease? Okay, so you can work together, and I'll just spend a little time in each quadrant, and you can watch, okay? So go. You're doing part B, 4B. So here's quadrant 2. Oh, shoot. Turn that off. Okay, here we go. Quadrant 2. Okay. Talk amongst yourselves. Work together. So here's quadrant 2. What is the vertical distance doing? And what do changes in vertical distance do? Sorry. TOS. Okay, there should be lively conversation. What does the vertical distance do? What do changes in the vertical distance do? One more time on this one. What does the vertical distance do? What do the changes in vertical distance do? Sorry. Okay, so here's quadrant 3, or from 9 o'clock to 6 o'clock. What does the vertical distance do? What do the changes in vertical distance do? One more time from 6 to 9. What does the vertical distance? Does it increase or decrease? Do the changes in vertical distance increase or decrease? Are the changes positive or negative? Are the changes in the vertical height positive or negative? They're negative. Are they becoming more negative or less negative? Less negative. So are the changes increasing or decreasing?
Changes are increasing.
The changes are increasing. The vertical distance is decreasing. That means these changes are negative. Are they becoming more negative or less negative? Less negative. Here's from here to here, that's the first change. It's the highest negative change. Then there's a smaller negative change, then a smaller negative change, then the smallest negative change. So you have negative changes that are getting less negative, so the changes are doing what? Increasing. This is that counterintuitive thing that we've been practicing. Okay, last section. Okay, is the vertical distance increasing or decreasing? Vertical distance. It's increasing, right? Vertical distance is increasing. It starts at what? What's the vertical distance start at? Negative 2.6 and ends at 0. So it increases from negative 2.6 to 0. The changes, are the changes positive or negative changes? So from here to here, is the change in the vertical distance positive or negative? Oh, seems like we're not sure. If the bugs, yeah, they're positive. If the bug is, if his vertical distance is increasing, which it is, the vertical distance is increasing, then those changes are positive changes. Going up, right? Going up means positive changes. And what are those changes increasing or decreasing? They're increasing. So, yeah, so the changes are becoming more positive. So they're increasing. Okay? So in the first quadrant from 3 o'clock to 3 o'clock to 12 o'clock. What's that? So in the first from 3 o'clock to 12 o'clock, is the height increasing or decreasing?
Height increases.
Height increases. Changes? decrease. So we get a rising concave down graph. Second quadrant. Is the height increasing or decreasing? Decreasing. Are the changes increasing or decreasing? More negative. Therefore, decreasing changes. This is, you gotta snap out of your tiredness and say, I gotta work on this because I still think these changes are increasing, but they're not. Here, the changes are decreasing. Why? Because they're becoming more negative. So all through this first half of the circle, what are the changes doing? Decreasing. They're becoming less positive and more negative, and therefore the graph is what shape? Concave down. Concave down. Do you see? All through here, the changes are decreasing, and therefore the rate of change all through here is decreasing rate of change. Decreasing rate of change. Okay? From 9 o'clock to 6 o'clock, vertical distance decreases or increases?
Vertical distance
Decreases. Changes? They're negative changes. Less or more negative? Less negative. Therefore, changes are increasing. Changes are increasing. Finally, the vertical distance increases and the changes are also increasing. They're becoming more positive as it goes back to 0. So I can show the whole thing here. So let's talk about angles here. So what was our angle as it went from 3 o'clock to 12 o'clock? That was our 4, right? 4/16. So halfway around was 8. And then all the way around. Easy to convert to radians, right? Halfway around, 8/16 of the circle is how many radians? That's our pi. So if we want to do this in radians instead, which is what we want from now on, okay, so what angle is 4/16 of the circle? Pi over 2. Okay, and then 3 pi over 2. Full circle? 2 pi. The height at the top of the fan? 2.6. The vertical height when the bug's at the bottom? Negative 2.6. Okay? Okay, the next one is harder. Why is the next one harder? Because this one's nice and easy because our y-axis is the vertical height of the bug. Now we're still going to make this graph, but now the y-axis is going to be horizontal distance from the vertical diameter. Okay? So it's more confusing because this lines up real nice, right? That y-axis just lines right up with the circle and the vertical distance. But now we're going to track horizontal distance and we're putting on the vertical axis. Do you see? All right. But I've got the tool to help you. Here we go. So now this is, they don't do it out as, but you're gonna do it yourself. This is going to be the graph for number 5. We're going to illustrate how the horizontal distance to the right of the vertical diameter covaries with the measure of the angle. So our input is angle still. Output is, now we're going to do horizontal distance right of vertical diameter. Okay, same 2 questions. in each, so as the bug goes from 3 to 12 to 9 to 6 o'clock position on the clock, does the output increase or decrease? And second question, do changes increase or decrease? So I'll do the first quadrant first, get a partner, talk it out, and I'll just spend a little time in each quadrant. Ready? Here we go. So, first quadrant. Oh, I gotta turn it on, hold on. I'm gonna turn the axes on. Okay, there we go. Here we go. First angle. So how am I showing the actual, where on this diagram am I showing the horizontal distance of the bug? Where am I showing the horizontal distance of the bug here? Yeah, so how in this animation am I representing the horizontal distance, the actual horizontal distance of the bug? Nope. Kind of, but there's a more obvious place. I'm representing the horizontal distance of the bug. Right, the red bar, right? The red bar, sorry, this is very not. The red bar is showing the horizontal distance of the bug. How am I representing changes in the horizontal distance? The dots, and then each black segment is the current change. So answer the two questions. Is the output increasing or decreasing? Are changes increasing or decreasing? Go. Answer them. One more time. So is the output increasing or decreasing? Are the changes increasing or decreasing? Just do them separately. Yeah, don't make those phrases. It just makes you confused. So just do them separately. Okay, how about the output? Is it increasing or decreasing? So what I hear mostly is creasing. So is it increasing or decreasing? Decreasing, good. Okay, changes. Are the changes increasing or decreasing?
Decreasing, because they're becoming more negative.
More or less, everyone think about it to themselves or talk to a person next to you. Are they becoming more or less negative or positive? Go. More or less negative or positive? All right, what did you conclude? More or less negative or positive? More negative. Therefore, decreasing changes. Decreasing changes. Okay, next part. One more part. Here we go. Is the horizontal distance increasing or decreasing? Still decreasing, right? Are the changes increasing or decreasing?
Changes are increasing.
They're becoming more or less positive or negative? Less negative. They're negative and becoming less negative. Therefore, changes are increasing. So, what will the graph look like? Where will it start?
Start at 2.6.
It'll start up at 2.6. And it'll decrease with decreasing changes.
So, yeah.
And then it'll continue to decrease with increasing changes. That's the first half. Let's do page 273. That's review. Let's do it for Friday. Page 273, we'll do it for Friday.